Hi everyone, my name is Lydia and this is what I wish they had taught me about econometrics and introduction. So far, we've been talking a lot about the matrix notation of the OLS. In this particular video, we're going to focus on matrix tricks used that you absolutely need to know. In this first part of the video, we're only going to go through the first 5 tricks, and these are the 5 mechanisms behind most derivations. Think of this list of 5 tricks as a little bit of a checklist before you go on and do any of the operations that you need with your matrices. The first one, it's the dimensions rule, which we have seen quite a lot actually in our previous videos, especially in the introduction to the matrix notation of the OLS. Before multiplying, always check the dimensions. In this particular case, it means that we always have to make sure that if our first matrix has dimensions n times k, then the next one needs to start with the dimension k, and the rest could be anything, let's say k times 1. In this particular case, you can go ahead with the multiplication, and the final dimension of your result will be n times 1. This is exactly how you compute the fitted values. So keep in mind, this is a very important rule that you always need to make sure you double check. The second one is the transpose of a product. It is very commonly used, especially when we do the minimization problem on the quadratic expansion, or also in the actual formula of the OLS, we are using the transpose all the time. Now, the transpose of a product, it's a very simple rule that you need to remember. So if you have a matrix A and a matrix B being multiplied, the transpose of that product is B transpose times A transpose. Keep in mind, there is one case where you see the application of this in your OLS formula, and that is, for instance, when you have X transpose X, all of it being transposed. In this particular case, the transpose will be exactly X transpose times X. The reason why behind this is because reversing and transposing, basically, it's leaving the whole thing unchanged. Okay, so reversing and transposing leaves it unchanged. The quadratic expansion is the next trick. So this identity is the secret behind the OLS derivation, and in the previous video where we showed the actual derivation, I gave you an identity that you had to remember. So I am going to rewrite this property all over again here for your ease of reference, and keep in mind this is what is used when you begin to write the minimization problem in matrix notation. So that is A minus B transpose times A minus B. Keep in mind A and B here can be matrices and or vectors. It's equal to A transpose A minus 2A transpose B plus B transpose B. Okay, this is very important, and this is what leads directly to our formula for the OLS. Moving on to trick number 4, the OLS normal conditions. We have actually given you a video that shows the full proof of that. Keep in mind, we have called the normal equation, or equations, since we are working with a matrix. So technically we're not finding just one beta, we're finding all of the betas at the same time. The normal equations are introduced by X transpose X beta equals to X transpose Y. From here, keep in mind, everything in multivariate OLS comes basically from these two symbols. This X prime X, again, a reminder, this is your regressor geometry. And the X transpose y, this is the correlation between your regressors and the y's. If you remember, and this is just to make the connection with the scalar version of your beta OLS formula, for most of you, you might remember the beta OLS is the covariance of the x and y divided by the variance of the x. Well, the x transpose x is basically the variance of x of this formula, while the x transpose y is the covariance of x and y part of this formula. So you are technically always giving the same information. It's just one, it's in scalar or in word version, and this is the matrix notation, which makes it a lot easier to make the connection with the projections concept. Lastly, the fifth tip, which we have reiterated in previous videos as well, it's very important: invertibility. The new concept that I am going to introduce though in this video, and I think it's very important to keep in mind, is this idea of a full column rank. Okay, so for the fifth trick, what you have to remember is that the matrix X transpose X is invertible if and only if X has a full column rank. If you remember in the previous videos, we said that if this matrix is actually not invertible, then we have what we called a multicollinearity problem, because it was very likely due to the fact that some of or one of the x variables in your x matrix was a linear combination of the other x variables. Now, when you don't have such a linear combination, we say that X has a full column rank. So this is, again, equivalent to saying that basically the columns are linearly independent. Okay. Now, the intuition, again, is if one regressor is one exact linear combination of the others, then this entire matrix is going to collapse into one direction. It means it cannot be inverted, and we won't be able to do the computations necessary to get to the unique solution that we need for our OLS. Thank you for following the first 5 tricks that are mostly used with matrix notations. We will see you in the next video with an additional 5 tricks.